Welcome back, everyone, to the Deep Dive, continuing our series from electron to grid. Hard to believe we're already at episode 4 of 12.
It flies by. We've laid some serious groundwork, haven't we? Covered electrons, voltage, current, resistance.
And last time, active power, P, the kilowatts, doing the actual work, lighting things up, spinning things around, the useful stuff.
Exactly. The power that gets the job done.
Okay, let's unpack this next layer then.
Yeah.
Because the grid, well, it carries more than just that useful power. Today we tackle its necessary but often misunderstood twin, reactive power, Q.
Yes, Q. The invisible support system. We've looked at sources that really try to, demystify this. It doesn't do work itself, but modern power systems simply can't operate without it.
Right, so what's the mission today? What do we want listeners to really grasp?
The goal is understanding why. Why do power systems need to handle more current than seems necessary for the work performed? We'll break down the components, active, reactive, and apparent power.
And crucially, the cost of not managing it well, right? The power factor. Absolutely. How utilities measure efficiency or inefficiency, and why it hits the bottom line, especially for industrial users. It's all tied to the infrastructure burden reactive power creates.
Okay, this sounds like we need an analogy right off the bat. Active power, P, does work. Reactive power, Q, doesn't, but is needed. Help us visualize this.
Let's go with the classic one, the beer mug analogy. It works pretty well here.
Okay, I'm thirsty already. Lay it on me.
So you order a nice big beer, the actual liquid beer you're going to drink, that's your active power, P, measured in kilowatts. It's what you actually paid for, what does the job.
Got it. The good stuff.
Right. But pretty much any draft beer comes with some foam on top, doesn't it?
Always. Sometimes more than you'd like.
That foam, that's your reactive power, Q.
Yeah.
Measured in kDAR kilovolt amps reactive. It takes up space in the mug, but, well, it doesn't quench your thirst.
Okay. So Q is the foam. It's there, takes up space, but isn't the main event.
Exactly. And the entire mug, the glass itself, that has to be big enough to hold both the beer and the foam. That's the apparent power. S, measured in kVA, kilovolt amps.
So apparent power is the total size requirement, the total capacity the system needs to handle beer plus foam.
Precisely. The utilities wires, the transformers, the generator, they all have to be sized for S. The apparent load, not just P, the useful load. Too much foam means you need a huge, expensive mug just to get a decent amount of beer.
Okay, that clarifies the what, now the why. Why do we even have this foam, this reactive power Q? Why can't we just have pure beer, pure active power?
Great question. The need for Q, for reactive power, comes primarily from devices that use magnetism to work. We're talking about inductive loads.
Inductive, like induction motors, transformers, stuff like that.
Exactly. Motors, generators, transformers, the workhorses of industry, they rely on electromagnetism. To make a motor spin or to change voltage in a transformer, you need to create and sustain a magnetic field.
And that magnetic field requires?
It requires current, but it's a specific kind of current demand. Reactive power is essentially the energy oscillating back and forth between the source and the load that energizes that magnetic field. It doesn't get consumed as heat or work. It just shuttles back and forth to keep the field alive.
So without Q, an induction motor just sits there. No magnetic field, no spin.
Correct. It's inert without that reactive power support.
Okay, here's the part that always seemed counterintuitive based on the sources. If it's so essential, why can't the power plant just generate the Q along with the P and send it down the line? Why all the fuss about managing it locally?
The transmission problem. Physics gets in the way. Specifically, the impedance of transmission lines. It's resistance and reactance combined.
Okay.
The sources are really clear on this. Trying to transmit reactive power, Q, over long distances is incredibly inefficient. You get massive losses, not just heat losses like I squared R, but what we call I squared X losses, where X is the line's reactance.
So shoving VARs down a long wire causes huge waste.
Worse than waste, actually. It causes a significant voltage drop along the line. The further you try to push Q, the lower the voltage gets at the receiving end. Try to push it too far or push too much, and the voltage can collapse entirely.
Collapse, like the lights go out, the motors stop.
Exactly. A voltage collapse. It means the system can no longer maintain adequate voltage to supply the load. So trying to centralize Q generation and transmit it is basically impossible for a stable grid.
Wow. Okay, so the fundamental rule is reactive power must be supplied close to where it's consumed, locally.
That's the golden rule. Generate it or provide it near the inductive loads, near the motors, the factories, the large commercial buildings.
Which brings us back to the beer mug. If you have too much foam locally, you need a bigger local mug. How do we measure that foam to beer ratio?
That's the power factor, PF. It's simply the ratio of the real work being done, the active power, P/kW, divided by the total apparent power the system has to carry, the apparent power, S in kVA.
So PF equals kW kVA.
Correct. And you want that ratio to be high, ideally close to 1.0, or unity. A power factor of 1 means all power being delivered is active power, all beer, no foam. A low power factor, say 0.7, means only 70% of the current is doing useful work.
And the other 30% is that reactive current, just sloshing back and forth, supporting magnetic fields, but requiring larger infrastructure.
Precisely. A load with a low power factor draws more total current from the grid to do the same amount of useful work as a load with a high power factor.
More current. Okay, let's dig into why that's bad. What are the real consequences of that extra current?
Well, first, basic physics. Current flowing through wires creates heat. That's the I²R loss, resistive loss. More current means more heat, which is literally wasted energy. Energy the utility generated, paid fuel for, and now it's just heating up the wires instead of doing work.
So inefficiency and wasted money on energy. What else?
The bigger issue, often, is the infrastructure capacity. That higher current requires thicker wires, larger transformers, bigger circuit breakers, more robust switchgear. Everything in the delivery chain has to be oversized to handle the apparent power, S, not just the useful power, P.
So the utility has to invest more capital and bigger equipment simply because a customer's load is inefficiently drawing reactive power.
Exactly. And that capital cost gets passed on. This is why utilities penalize large industrial and commercial customers for having a low power factor.
The infamous power factor penalty.
Yep. They might charge higher rates per kilowatt or add a specific surcharge based on how low the PF drops, often below a threshold like 0.95 or 0.9.
Right.
Those penalties can be substantial, sometimes even more than the cost of the actual energy used.
Because the penalty reflects the utility's increased infrastructure cost to serve that inefficient load, it's basically saying, you're making us buy a much bigger mug for your beer, and you're going to pay for the oversized mug.
That's a perfect way to put it.
Now, you mentioned this relates to the timing of voltage and current in AC systems. I remember something from physics class. ELI, the ICE man. Sounds like a questionable cartoon character.
Huh, it does. But it's a super useful mnemonic. It describes the phase relationship between voltage E and current I in inductors, L, and capacitors, C.
Okay, break it down. ELI.
In an inductor L, like our motors and transformers, the voltage E leads the current I. So ELI, the current waveform lags behind the voltage waveform. This lagging current is characteristic of inductive loads and results in a lagging power factor.
Which is the most common problem, right? Because industry is full of motors.
Overwhelmingly the most common scenario.
Okay, so what about ICE?
In a capacitor C, it's the opposite. The current I leads the voltage E, ICE. Capacitors cause a leading power factor.
Got it. ELI. Voltage leads current in inductors, lagging PF. ICE. Current leads voltage in capacitors, leading PF.
Exactly. And this phase difference is fundamentally what reactive power is and why power factor matters. The goal is to get voltage and current back in sync, or as close as possible.
So if our big problem is lagging power factor caused by inductive motors, ELI, the solution must involve capacitors, ICE.
You got it. That's the core principle of power factor correction, or PFC. If you have too much inductive load causing lag, you install capacitors locally to introduce a leading effect. The capacitor supplies the reactive power the inductor demands.
So the capacitor provides the foam locally, so the utility doesn't have to send it down the line and oversize everything.
Precisely. You're essentially canceling out the inductive reactive power demand with capacitive reactive power supply right there at the facility. This reduces the total current drawn from the grid and brings the power factor closer to unity.
Okay, so how is this done in practice? What do these correction methods look like?
Well, the methods generally fall into two buckets.
Yeah.
Static, meaning relatively fixed or slow acting, and dynamic, meaning fast acting.
Let's start with static. What's the typical approach?
The most common static solution is installing capacitor banks. Literally, banks of capacitors connected to the electrical system, often at the main service entrance or near large motor loads.
Are they just always on?
They can be fixed, meaning always connected, or switched. Switched capacitor banks turn on and off in stages, often automatically, based on the measured load or power factor. There are also things like tap-changing transformers or fixed reactors for specific situations, but cap banks are the main tool for lagging PF.
And these are good for loads that are relatively stable.
Yeah, they're great for handling predictable changes in load over, say, seconds or minutes. Think of a factory floor where large machines turn on and off. They're cost-effective, reliable, standard technology.
But our grid isn't always predictable anymore, right? With wind and solar power fluctuating rapidly and maybe more complex industrial processes, sometimes you need faster correction.
Exactly. That's where dynamic compensation comes in. When you need a response time measured in milliseconds, not seconds or minutes, static solutions aren't enough.
What are the options for dynamic compensation?
Historically, one method was the synchronous condenser. It's basically a large synchronous motor running without a mechanical load, just spinning to either generate or absorb reactive power by adjusting its field excitation.
Kind of like running a generator just for the foam. Seems inefficient.
It has its drawbacks, yeah. Maintenance losses, which is why the modern approach, highlighted in the sources, is increasingly the StatCom.
StatCom, static synchronous compensator. Sounds fancy and expensive.
They are definitely more complex and costly than static capacitor banks, yes. But their capabilities are on another level, especially for grid stability.
Okay, so what makes a StatCom so special? Why is it worth the cost in certain applications?
Several key things. First, speed. They react almost instantaneously within milliseconds to changes in system voltage or reactive power needs. Second, they are dynamic and continuous. They can provide exactly the amount of reactive power needed smoothly, not just in fixed steps like switched capacitor banks.
And crucial.
They are multi-quadrant. This is huge. Unlike a capacitor bank, which can only supply capacitive reactive power, leading VARs, a StatCom can both supply capacitive VARs and absorb inductive VARs, lagging VARs.
So it can act like a capacitor or an inductor very quickly.
Exactly. It provides complete flexibility in reactive power control.
How does it do that? What's the technology inside?
It uses power electronics, specifically a voltage source converter, or VSC. Think of it as a very sophisticated inverter, similar to what you find in solar installations or variable speed drives, but operating at high power levels.
And this VSC creates a voltage.
Yes, the VSC generates an AC voltage waveform that's synchronized with the grid voltage in frequency and phase. The magic happens by controlling the magnitude of the StatCom's internal voltage relative to the grid voltage.
Okay, walk me through that. If the StatCom voltage is higher than the grid.
If the StatCom's voltage magnitude is slightly higher than the system voltage, it pushes reactive current out onto the grid. It acts like a capacitor, supplying VARs.
And if its voltage is lower?
If its voltage magnitude is slightly lower than the system voltage, it pulls reactive current in from the grid. It acts like an inductor, absorbing VARs.
And it can adjust this voltage difference very precisely and very quickly.
Extremely quickly and in very fine steps. This allows it to provide smooth, continuous, and bidirectional reactive power flow.
Why is that speed and flexibility so critical for the modern grid? Give us an example.
Think about a fault, like a short circuit on a major transmission line. When that line suddenly trips out, the power flow shifts dramatically onto parallel lines, and the voltage in that area tends to sag, sometimes severely.
Okay, a sudden voltage drop.
A static capacitor bank might switch on a step eventually, but it's slow. A StatCom, located nearby, sees that voltage drop instantly, and within milliseconds, injects a large amount of capacitive reactive power to prop the voltage back up.
Like a shock absorber for voltage.
Exactly. It provides dynamic voltage support during the disturbance, helping to maintain power flow, preventing the voltage from collapsing further, and stopping the disturbance from cascading into a wider blackout. It significantly enhances grid stability and resilience.
So StatComs are really about handling those fast, unexpected events that could destabilize the grid, especially with more variable generation online.
That's a primary driver for their increasing deployment on transmission systems, yes.
Yeah.
They are key tools for managing the dynamics of the modern grid.
Okay, so wrapping this up. This deep dive really underscores that reactive power, Q, this foam in our analogy, isn't just some inconvenient byproduct. It's not wasted energy in the traditional sense.
Absolutely not. It's the essential, non-work-performing current required to establish and maintain the magnetic fields in all the motors, transformers, and inductive devices that underpin, well, pretty much our entire industrial society.
And managing it properly, generating it locally, using capacitor banks for steady loads, deploying advanced tools like StatComs for dynamic stability is crucial.
It's vital. It minimizes that excess current draw, which means less energy wasted as heat, allows for smaller and less expensive wires and equipment, avoids those costly utility penalties, and keeps the grid stable.
It really touches everything from the physics of electromagnetism right down to your electricity bill, potentially.
It does. Which leads to a final thought, maybe a provocative question for you, the listener, and for grid planners everywhere.
Okay, let's hear it.
We've talked about how complex and expensive these dynamic compensation devices like StatComs are. They offer near instantaneous voltage support and stability. But the question becomes, how much is society, how much are we willing to pay for that level of instantaneous high-speed grid stability?
Versus what? Just accepting minor hiccups.
Versus perhaps accepting slightly slower responses, maybe occasional temporary voltage dips during disturbances, by relying more on less expensive, slower-acting solutions. It's a constant balancing act, isn't it? Between the need for speed, the technological complexity, and the overall cost of keeping the power flowing perfectly smoothly all the time. Where do we draw that line?
That's a really interesting trade-off to consider. Speed, complexity, cost, and reliability. Something definitely to think about. Thanks for breaking down reactive power today.
My pleasure. It's a critical piece of the puzzle.